Okay. Good morning, students. Today we will talk about the conduction of sound. I would be introducing to the auditory physiology. So to start with, what are today's learning objective? So we would discuss something regarding physics about the sounds, that is acoustics. Then we should discuss about the functional anatomy of the ear. Then what is the function of auricle, external auditory meatus, and then the middle ear. So what is the function of ear? Means what does the ear do to us? Is it only hearing or something else? Yes, it is also concerned with balance. So for hearing, how does it do? It is with the help of these structures. Okay, so this is what is the outer ear, this is the middle ear, and this is the inner ear. And for equilibrium, what we need is inner ear. So this cochlea takes takes care of hearing, and this will take care of the balance, that is the semicircular canals. And the receptors for both activities are hair cells. So hair cell is concerned not only with hearing but also with equilibrium. Of course, the location of the hair cell differs as per the function. For hearing, the hair cells are present in the cochlea, whereas for equilibrium or balance, the hair cells are present in semicircular canals. Now, what is sound? I hope everybody is familiar with this friend, that is early morning, the alarm rings. So when the alarm rings, what happens is it produces sound. So here we see the sound waves. Now what exactly is sound? So as you see here, this is what is the external environment or the atmosphere. So as the sound wave moves, here the arrangement of the molecules changes in the atmosphere. So that is, the longitudinal vibrations are created in the external environment or atmosphere, which corresponds to alternate phases of condensation, that is this dense portion, and rarefaction, that is where the molecules are dispersed. So let us see some features of sound. So here if you see this typical sound wave, this wave is compression and this is rarefaction. So wavelength. Now if you look at wavelength, it is nothing but it is a distance between consecutive corresponding points. For example, if you take the tip of this wave, so from this point to this point is wavelength. So if you take, for example, point over here, so from here to this point would be wavelength. So it is a distance between the corresponding points on the same phase of the wave. The height of this crest is the amplitude. Now, other features of the sound waves are speed, next is frequency, amplitude, pure tone, complex sound, overtones, or noise. Now let us see what is speed. So for example, here there is a person who is doing a gunshot, and there is another person who is having a watch. The moment he shoots, he'll record the time here, and when he hears, that is what is the distance. So speed is nothing but the distance traveled per unit time by that sound wave. And this speed depends on the type and the properties of the medium. So as we know, we have different properties, that is either solid, liquid, or gas. So if you see the speed of the sound in different material, here in the air it is 331.45 meters per second. In water it is 1496. If you see in bone, it is 4080. Whereas in steel, which is a metal, it is around 5940. So if you look here, as the density of the medium increases, the speed of the sound also increases. Now next is frequency. Now frequency is nothing but the number of cycles generated in 1 second. So if you look here, this is what is high frequency, and compared to this is low frequency. Now why frequency is required? Because frequency corresponds to the pitch. Now usually females are high pitched and males are low pitched. Now, next property is, coming to frequency only. In the audible frequencies, for humans, it ranges from 20 hertz to 20 kilohertz or 20,000 hertz. If the sound has a frequency less than 20 hertz, it is known as infrasound. Now, animals like elephants are capable of hearing even the infrasound, that is, the sound with a frequency less than 20 hertz. Whereas sounds with frequency more than 20 kilohertz is known as ultrasounds. As we all know that bats have ultrasonic acoustics. And the greatest sensitivity for human ranges between 1000 to 4000 hertz. Though the range is from 20 hertz to 20 kilohertz, the greatest sensitivity is from 1000 to 4000 hertz. Now coming to the next feature. Now look at this bird who is chirping. If you look at the height of the waves, they are very small. As compared to this bird who is screaming, look at the amplitude. These are the bigger ones. So amplitude is nothing but it corresponds to the loudness of the sound. Now coming to pure tone. Pure tone is nothing but a sound of a simple sinusoidal waveform. So if you look at here, here in this A, all the waves are of same size. If you compare A and B, the size is increasing in B, but the waves again are of the same size. So in pure tone, we will have one particular frequency. The best example is use of this vibrating tuning forks for sound. So 128 hertz tuning fork will give you a sound of 128 hertz. Similarly, 256 and 512. Each tuning fork will produce a sound of one frequency only. Now, what is the difference between pure tone and complex sound? So if you look at here, this is a tuning fork which is producing sound of, waves of same size. Whereas coming to flute, if you see here, this is composed of three different waves who are compiled as one waveform. So complex sound is nothing but it is the sum of pure tones. So here the three waves are becoming one tone. But if you look at the arrangement here, they are arranged in an orderly fashion. Similarly for violin, if you look at these waves, different waves but arranged in orderly fashion. Means a wave of different frequency amplitude are arranged in orderly fashion. Then when the sound becomes noise, a very typical example, if the teacher is not there in the classroom, this is what you people do. You create sound. So in sound also, different frequencies come together, but they are completely disorganized. So completely disorganized tones constitute noise. Now, what exactly is decibel? We always talk about, sound more than 100 decibels are not allowed, especially during festivals and all. Now, what exactly is decibel? As we know, pitch means corresponds to frequency. Now, amplitude means the height of the wave. That is nothing but the maximum pressure which is exerted at the eardrum to produce some change. And usually, this is expressed in terms of decibel. Now, decibels is nothing but it is defined like it is the intensity of sound in bells is defined as a logarithm of ratio of intensity of that sound and a standard sound. Now, usually we take this unit, that is decibel, which is nothing but 0.1 bell. Now, does 0 decibel mean absence of sound? No. It is nothing but it is the average auditory threshold for humans for 100 hertz. So 0 decibel means some sound is of course produced. It is not absence of sound. Now let us look at this chart which is ranging from 0 decibel to 140 decibel. Now look here. For normal respiration, sound of 10 decibels is produced. If you whisper, it is around 30 decibel. The sound of rain produces rain produces sound of 50 decibel. A normal conversation is around 60 decibel. In traffic, it ranges between 70 to 80. Trumpet blowing is around 110 decibel. Now, whereas you look at the takeoff of a flight, it is 130, and the firecrackers produce sound of almost 140 decibel. Now, why this is important? Because 40 corresponds to faint, a normal conversation is moderate, whereas when it comes to trumpet blowing, it is extremely loud, and at 140, the threshold for pain reaches. Now, more than 85 decibel is harmful, and if the sound produces more than 100 decibel, it will of course produce damage to your auditory apparatus, that is the cochlea, and more than 140, that will create pain. Now let us see what happens when sound reaches the ear. Now, for the sound to reach here, the sound energy has to get converted into mechanical energy, that is at the level of tympanic membrane. Now, from the tympanic membrane to the foot plate is the middle ear. Now, in the middle ear, the sound energy gets converted to mechanical energy. Once the foot plate is set into vibrations, cochlea is a place where the mechanical energy will get converted to electrical energy. And once the electrical energy is formed, the sound is transmitted in the form of nerve impulses along the pathways to the brain. Now let us understand the functional anatomy of the auditory apparatus. Now, it is divided into outer ear, middle ear, and inner ear. Now, outer ear consists of pinna and auricle and ear canal. Ear canal is also known as external auditory meatus. Now, the middle ear starts with eardrum, also known as tympanic membrane. It consists of three ossicles, that is malleus, incus, and stapes. Now, inner ear consists of cochlea and semicircular canal. Now, this cochlea is further enlarged into the cross-sectional area where these hair cell, this is a place where the conversion of mechanical energy into electrical energy takes place. So this is the receptors for sound. Now let us see each in detail. Now coming to auricle. This structure which is green color is known as auricle. Now as you see, it has got a peculiar shape. Now the shape of the auricle helps in detection of direction of sound. Now this auricle helps to channel the sound waves from the atmosphere to the external auditory canal. Also, it seems it helps in funneling of the sound waves. So, it captures more waves and energy. In this way, it enhances the sensitivity to hearing. Now, the next structure is external auditory canal, the green colored here. Okay. So, the job of the external auditory canal is to conduct the sound waves from which are focused from the auricle towards the tympanic membrane. Now this is not a straight canal, it is S-shaped. Now presence of S-shaped canal prevents direct mechanical injury to the tympanic membrane. Also, this canal maintains normal humidity and temperature, which is favorable for normal functioning of the tympanic membrane. Coming to middle ear. Now as you see middle ear, this is what is tympanic membrane. Okay, so this is a very thin membranous sheath which is held in position posteriorly with the handle of malleolus. Now the three ossicles in the middle ear are malleus, incus, stapes. Now stapes is attached to the foot plate. The foot plate of the stapes is attached to the oval window and the eustachian tube. Now eustachian tube is an opening from the middle ear towards the nasopharynx. Now the middle ear ossicles, here you see the arrangement. Now this is what is stapes, where the foot plate is attached to the oval window, and here there is another opening known as round window. The importance of these structures will be discussed in the later part of the class. Now coming to the muscles of the ear, middle ear. Now there are two important muscles, that is tensor tympani, this one. Okay, so this tensor tympani anchors the malleus to the middle ear, and it is supplied by the trigeminal nerve. The next important small muscle is stapedius, which is supplied by seventh cranial nerve. So this anchors the stapes to the middle ear. Now, the muscles and the ossicle form a lever system which is quite flexible to modulate the sound amplitude. Uh, Now, coming to the functions of the middle ear. There are three important functions of the middle ear. First is conduction of the sound wave, that is from the external environment towards the cochlea. To do this, we have to do impedance matching and attenuation reflex. Now, conduction of the sound wave. Now, once the sound strikes the tympanic membrane, this is what happens. So, as each sound wave strikes the tympanic membrane, the ossicles start moving in a orderly fashion. And if you look at this foot plate, it is coming in and out at the oval window. So this whole process is quite complex. Now, if you understand for the conduction, we need two important things. That is eustachian tube, which should be well functioning. Now, eustachian tube should maintains ventilation of the middle ear. It ensures that for adequate conduction of sound, the middle ear pressure is equalized to the atmospheric pressure. I think especially when you all travel in flight, you hear some popping sound. I mean, so that is nothing but it is due to the retraction of the tympanic membrane. And many a times, if you feel that the tympanic membrane is retracted, they ask you to blow with the nose closed. So in this fashion, the pressure is exerted on the tympanic membrane via the middle ear, and then you hear that popping sound. And next job is a normal functioning tympanic membrane. Now this tympanic membrane acts as a pressure receiver. Means it will, the sound wave is a form of energy which generates some pressure. So this tympanic membrane will receive that pressure. Resonator means it will vibrate depending on the type of sound wave which is striking it. And then critical dampening. Once a sound wave strikes, it will vibrate only once and then stop. So that as the number of waves keep on striking it, for example, 5 sound waves have struck the tympanic membrane will vibrate only 5 times. So this is what is the job of the tympanic membrane. Now coming to next. Now as we know that the middle ear cavity is filled with air and the cochlea is filled with fluid. Now the sound has to travel from air to the fluid. Now this is a tedious job. Now for example, this is a man who is sailing on a boat and this is a diver under the sea. Now usually if this man tries to talk with this diver, what is going to happen? 90% to 95% of the sound will get reflected at this interface itself. Hardly 1 to 5% of the sound will reach this diver. So the same problem is faced at this interface. That is at the foot plate. Means the sound from the middle ear, which is air filled, has to reach this inner ear, which is fluid filled. Now to solve this problem, this middle ear requires some mechanism, and that is nothing but impedance matching and the phase differential between the oval window and the round window. Now let us see what is impedance matching. So as you see here, as the sound strikes, the ossicles move and the footplate also moves. Now, as the inner ear is filled with fluid, it has got high inertia. So the same sound will require more force, pressure to move the fluid which is filled in the inner ear. So impedance matching is nothing but it is a capacity to harness this sound wave's inherent energy. Okay, means it will try to preserve all the sound waves energy and then transmit it to the inner ear with sufficient force. Now this is achieved with the help of this ossicles. Okay, and the second place is this oval window. So at this oval window we have to increase the pressure so that that much level of vibration is generated in the inner ear. Now coming to next, let us see what is the lever action. Now in the middle ear, this is a peculiar arrangement of the ossicles. The handle of the malleus is attached to the tympanic membrane. This is how the incus is attached to the malleus, and this is how the the stapes is articulated with the incus. So this is very typical. So if you see this pivot joint, it is not in the center. The malleus has got a larger contribution as compared to that of incus. So if you look here, the malleus length is almost 1.3 times than that of incus. Because of this shift in the pivot joint, the liver system is able to amplify the tympanic membrane by almost 30%. So 1.3 times it is increased. Now let us see how we can increase the pressure at the oval window. So as you remember, again and again I am insisting, the foot plate is attached at the oval window. Okay, so if you look at the size, this is what is the size of the tympanic membrane, and this is the size of the foot plate, or the oval window we can say. So there is a large difference. Now does this surface area make a difference in increasing the pressure? So to understand this, let us do some activity. So this is one female. So in case scenario 1, on Sunday you are reading a newspaper in the garden. A lady who is wearing sneakers, okay, the flats, who is walking, happens to put her steps on your foot. Now in second case, the same lady on Tuesday, when you are waiting for your friend outside the food court, now this time she is wearing heels and she accidentally steps on your foot while crossing you in the food court. So in both cases, because of the stepping of your foot by her footwear, you have pain. But in which case the pain is more? It is by this sneakers or by the heels? Of course, the answer is heels. Now why? Here, though, the look at the surface area of the shoe and this heel. Is there a difference? Yes. This is a bigger surface area and this is a smaller surface area. To understand this, pressure is equal to force by area. So if the force is same, that is your weight. If your area decreases, the pressure will increase. The same thing happens with this. Here the force is same, that is the weight of the body, which acts as a force, remains same. What changes here is the area. So here the area is less, so the pressure generated would be more. Here the area is more, so the pressure generated would be less. So for the same area, less pressure will generate more pressure. The same thing happens with the tympanic membrane and the oval window. Look here, again, the sponge. The brick, if it is placed horizontal, less force. If it is placed vertical, more force. So this is how area makes a difference in application of force. Similarly, it is easy to cut with a sharp knife rather than a blunt knife. So there are so many examples in our daily activity which explains the pressure, force and area relationship. So this is how we increase the pressure at the oval window. So this is what is tympanic membrane with an area of 55 square meters, and this is the footplate of stapes, which corresponds to the area of the oval window. So this is around 3.2 meters square. So if you see the difference, it is 17 times, the tympanic membrane is 17 times larger as compared to that of the footplate of stapes. That's why the pressure exerted on the oval window is amplified 17 times. Now let us add on the effect of the liver system, of the ossicles and the pressure. So for impedance matching, the lever mechanism of the malleus and the incus increases the force by 1.3 times. Because of the difference in the surface area of the tympanic membrane and the footplate of the stapes, the pressure exerted on the oval window is amplified 17 times. So the total force now is a product of 17 into 1.3. That is what is 22 times. So by these two mechanisms, we are amplifying the pressure. For example, one is the pressure exerted at the tympanic membrane, so which the same thing when it gets conducted on the footplate of stapes is 22 times. If there is absence of this tympanic membrane or the ossicles, sound can reach the cochlea, but the sensitivity reduces by 15 to 20 decibel. The second important thing is phase differential between the oval window and the round window. So here you remember this step is attached to the oval window, and this is what is a round window. Now, once the foot plate strikes here, I mean the oval window, the fluid is set into vibrations. It will reach the helicotrema, and from here the sound waves will travel through the perilymph again and strike at the round window. So striking, the sound waves will create vibrations from the oval window, and the round window does the job of receiving that pressure. I think here you can see it very well. Once the sound wave strikes the tympanic membrane, the ossicles start moving. The footplate will set vibrations in the perilymph here. When the footplate goes in, the round window pops out. So you can say that sound waves don't strike oval and round window simultaneously. So if the oval window is in the phase of compression, round window goes into stage of rarefaction. Now this acoustic suppression is achieved by the air cushion which is there in the middle ear and the tympanic membrane. Now coming to next. Now what exactly is tympanic or attenuation or acoustic reflex? Now here in this picture, if you see what is happening, this boy is blowing a horn on this, is suddenly blowing a horn, and this boy is surprised. Now this thing usually, I think we must have faced this scenario many a times in our daily routine. We usually get startled, or sometimes it is very annoying also. So whenever the sound, we get exposed to loud sound, this reflex comes into picture. Actually, acoustic reflex or attenuation reflex is a protective reflex, or we can also say it is a preventive reflex, because by this reflex we reduce the sound pressure which is exerted on the oval window. And the stimulus for this reflex is loud sound. Now for this reflex, the latent period is around 40 to 80 milliseconds. Now this is quite a brief period. Now what happens? Now whenever the loud sound strikes the tympanic membrane, there is reflex contraction of stapedius and tensor, mainly the stapedius, which anchors the stapes to the middle ear. So that makes the foot plate, very rigid, and to lesser extent tensor tympani, which anchors the malleus to the middle ear. So if this muscles makes the ossicle system rigid, what is going to happen? The sound conduction via this ossicles will reduce. So this lever system will become more rigid and will reduce the pressure of the sound which is being exerted on the oval window. So this is how exposure to loud sound causes this reflex and protects our cochlear membrane, the oval window from damage. But if there is sudden loud exposure to loud sound like the gunshot sound or the bomb explosion, due to the brief latent period of around 40 to 80 milliseconds, this reflex doesn't come into picture so early. So during that exposure, there can happen cochlear damage leading to sudden deafness. Now, what is the role of this attenuation reflex? So as I have been talking again and again, that its job is protection. So it is protection of cochlea whenever there is exposure to loud, intense sound. The stiffness of the lever system will reduce the sound transmission across the ossicle chain and reduce the pressure which is generated at the oval window. The second role is masking of low frequency of environmental sounds. So when the low frequency sounds are masked, it allows us to concentrate on a sound above 1000 hertz. As we know that 1000 hertz to 4000 hertz is the area where we have the greatest sensitivity. And the third most important is it serves as an adaptation just prior to vocalization and chewing. Means it dampens some sound which is produced during vocalization and chewing. So that's why whenever you chew, you don't hear that sound. But if you put on your earphones and you eat something, you can hear that sound more louder. So that is what happens. So this is what we have understood about air conduction. Means the air which is coming from the atmosphere, it strikes the tympanic membrane, it causes movement of these ossicles and then reaches the cochlea via the oval window. So this is what I have been talking around. Then how do you hear? I mean, you must have also heard about bone conduction. Now, what exactly happens? Now, when the bone conduction is coming into picture, there is no role of this tympanic membrane and ossicles. Then how still can you hear the sound? Now, if you look into this image, this bone vibrator is causing vibration in the whole skull. Okay, here, see. Now, where exactly is this cochlear labyrinth? Now, this is embedded in the bony labyrinth, which is a part of the skull. So, if the bone of skull bone is set into vibration, this will automatically set vibration of the fluid of the inner ear. So, this is how you hear the sound. For the sound to be converted into electrical energy, we have to set vibrations in the cochlea. So either it is via the tympanic membrane, ossicle, and then into cochlea, or the cochlea itself as a whole is set into vibration with the bone conductor. So either ways you hear the sound. The best example is vibrating tuning fork or the electronic vibrator, which is usually a part of the hearing aid in people who have extreme hear loss. So here, this sensor will receive the sound and then transmit this sound on the bone, which will cause vibration in the fluid in the cochlea. So this is how you hear the sound through bone conduction. So to summarize, I can say sound has got different physical properties. That is, it has got speed, amplitude. The amplitude corresponds to loudness. When it comes to frequency, frequency is nothing but the pitch. Higher frequency means higher pitch. Lower frequency means lower pitch. The next property is pure tone. Pure tone is nothing but it is a one type of frequency. Coming to complex sound is sum of different pure tones, which is organized in an orderly fashion. When it comes to noise, it is again different frequencies coming together but in totally disorganized manner. So whatever is the type of sound, it is received by the auricle and then focused on tympanic membrane. So the sound energy has to get converted into mechanical energy, and this occurs in the middle ear where the sound in the form of mechanical energy is relayed on the inner ear. And to do this job, we have role of impedance matching. Impedance matching where the lever system and the increasing pressure on the oval window, that does the job, and the phase differential between the oval window and the round window. And next is the role of attenuation reflex, which protects our cochlea from exposure to loud sound. Now, every time I have some questions, this time you all are not in front of me to answer this, but still I would like to ask, why do we have 2 ears and 1 mouth? So that we can listen twice as much as we can speak. Thank you very much for your patient listening.